No weapons, no armor. Yet this machine could become the most lethal platform ever conceived. It moves faster than bullets travel. No radar system on Earth can track it effectively. They whisper about it in classified briefings, calling it the Darkstar, and it's about to make every military strategy obsolete. For decades, experts claimed hypersonic aircraft were impossible. The physics didn't work. The materials couldn't handle the heat. The engines would melt before reaching target speed. But somewhere in the Nevada desert, engineers have been proving the impossible. Today, we're diving deep into America's most classified aviation project. Why are world superpowers terrified of this aircraft? What revolutionary technology makes it unstoppable? Let's uncover the truth behind the SR-72 right now. Military superiority has always depended on one fundamental principle: getting there first. The fastest army wins the battle. The quickest navy controls the seas. And in the skies, speed equals survival. But what happens when fast becomes instantaneous? When crossing entire continents takes less time than ordering coffee? When enemy forces can't even comprehend what hit them because it's already gone? This is the reality the SR-72 promises to deliver. We're not talking about being slightly faster than existing aircraft. We're talking about operating in an entirely different dimension of warfare where traditional defense systems become meaningless decorations. Hidden behind layers of security clearances at Skunk Works, something extraordinary has been taking shape. Not just an aircraft, not just an engine. An entirely new category of machine that shouldn't exist according to every physics textbook written before 2020. Picture walking into a facility where the impossible happens daily, where materials are created that can withstand temperatures hot enough to melt copper, where engines are printed, not built, with cooling channels embedded directly into their molecular structure, where computers make split-second decisions that would take human pilots several minutes to process. This isn't science fiction. This is Palmdale, California, 2025. Here's where things get absolutely insane. Every aviation expert will tell you the same thing. You can't build an engine that works efficiently from 0 to Mach 6. The physics are contradictory. Turbojets fail at high speeds. Ramjets can't start from standstill. It's like trying to design a car that performs equally well in city traffic and at the Indianapolis 500. Lockheed's engineers looked at this impossible problem and decided to solve it anyway. Their solution? Create an engine that literally changes its identity during flight. At takeoff, it's a conventional turbojet. As speed increases, it morphs into something completely different. By the time it reaches maximum velocity, it has become an entirely new type of propulsion system. The technical term is Turbine-Based Combined Cycle, but that doesn't capture the engineering wizardry involved. We're talking about an engine with multiple operating modes, each optimized for different speed ranges. Below Mach 3, it operates like a traditional turbojet. Between Mach 3 and 5, it transitions into ramjet mode. Above Mach 5, it becomes a scramjet. But here's where it gets even more complex. The transition between these modes isn't just flipping a switch. The engine literally reshapes its internal airflow patterns. Variable geometry inlet systems redirect supersonic airflow. Fuel injection systems switch between different operating modes. Combustion chambers adapt their burn characteristics in real time. Think about the engineering challenge. You're creating a machine that must function perfectly in 3 completely different operating environments, all while traveling at speeds that would tear apart conventional aircraft. The materials alone represent breakthrough technology. We're talking about components that can withstand temperatures exceeding 3,000 degrees Fahrenheit while maintaining structural integrity under enormous stress loads. The cooling system is perhaps the most revolutionary aspect. Instead of traditional cooling methods, the engine uses what engineers call transpiration cooling. Microscopic channels built directly into the engine walls that bleed cooling air through the metal itself. This technology was impossible to manufacture until recent advances in 3D printing allowed for complex internal geometries that conventional machining simply cannot achieve. The result is an aircraft that can taxi normally, then accelerate to speeds that make the Concorde look like it's standing still, all with the same power plant. And here's the terrifying part for America's enemies. This isn't theoretical anymore. Intelligence sources suggest working prototypes are already flying. But wait, it gets worse. For enemy forces, that is. The most radical aspect of the SR-72 isn't its speed or its stealth capabilities. It's what's missing from the cockpit. Nothing. No pilot. No human limitations. No biological constraints that would prevent the aircraft from performing maneuvers that would instantly kill any living creature aboard. Imagine an aircraft pulling G-forces that would liquefy human organs, executing attack patterns so complex that human reflexes couldn't keep up, making tactical decisions in microseconds based on data processing that exceeds human cognitive capacity by orders of magnitude. This isn't just removing the pilot to save weight. This is unleashing performance capabilities that were previously impossible because humans are, frankly, too fragile for this level of warfare. The artificial intelligence controlling these platforms doesn't get tired, doesn't panic under pressure, and doesn't hesitate when split-second decisions mean the difference between mission success and catastrophic failure. But it's not just basic AI we're talking about here. This is machine learning systems that have been trained on decades of combat scenarios, fed with real-time intelligence from multiple sources, and equipped with predictive algorithms that can anticipate enemy responses before human commanders even realize threats exist. The autonomous systems can process radar signatures, electronic emissions, visual imagery, and signals intelligence simultaneously while maintaining flight operations and mission objectives. Human pilots need years of training to master basic flight operations. The SR-72's AI systems can master complex combat scenarios in milliseconds. More importantly, these systems can coordinate with other autonomous platforms in ways that human-operated aircraft simply cannot match. Multiple SR-72s could execute synchronized operations across vast distances, sharing intelligence and adapting their missions in real time based on collective data analysis. The psychological impact on enemy forces cannot be overstated. Fighting against human pilots means fighting against predictable limitations and known decision-making patterns. Fighting against AI-controlled hypersonic platforms means facing an opponent that operates beyond human comprehension, with reaction times measured in microseconds rather than seconds. Development costs for the SR-72 program have reportedly exploded into territories that make even Pentagon accountants nervous. We're talking about billions of dollars invested in a platform that officially doesn't exist. Recent reports suggest cost overruns exceeding $335 million, which sounds enormous until you consider what this money is purchasing. Complete global reach within hours, intelligence gathering capabilities that make satellites look primitive, strike potential that arrives before enemies can activate their defense systems. When you're buying the ability to rewrite the rules of modern warfare, even astronomical costs start looking reasonable. Compare this to the $2.1 billion per B-2 Spirit bomber, and suddenly the SR-72's price tag seems almost modest for a platform that could revolutionize aerial warfare. The SR-72 represents something bigger than advanced aviation. It's the physical manifestation of America's network-centric warfare doctrine. Every sensor feeds into larger systems. Every mission integrates with global military networks. Every decision is optimized by artificial intelligence that processes information faster than human commanders can even read it. Picture this scenario. Suspicious activity detected anywhere on Earth. Within minutes, an SR-72 launches from an American base, arrives over the target faster than traditional intelligence networks can even confirm the threat exists, conducts detailed reconnaissance, and either neutralizes the problem or provides targeting data to other assets. The entire cycle happens faster than enemy forces can transition from peacetime to combat readiness. While America has been quietly developing hypersonic aircraft, other superpowers have been scrambling to respond. Russia's Kinzhal hypersonic missiles made headlines, but the Ukraine conflict revealed they could be intercepted by decades-old Patriot systems. China's DF-21D carrier killer missiles grab attention, but they're single-use weapons. The SR-72 is different. It's reusable, adaptable, and can be deployed repeatedly without the massive logistical burden of disposable systems. It's the difference between having a sniper rifle and having a guided bullet. Both can hit their target, but only one gives you sustained combat capability. But the competition isn't standing still. China's recent tests of their hypersonic glide vehicles suggest they're pursuing similar capabilities, though intelligence analysts believe they're still years behind American development. Russia's announced hypersonic programs have been plagued by funding issues and technical setbacks, particularly after international sanctions limited their access to critical technologies. European nations are pursuing collaborative hypersonic programs, but bureaucratic challenges and competing national interests have slowed progress significantly. Meanwhile, emerging military powers like India and Japan are investing heavily in hypersonic research, though their efforts appear focused on missile technology rather than reusable aircraft platforms. The real question isn't whether other nations can develop hypersonic capabilities. They will, eventually. The question is whether they can match the integrated systems approach that makes the SR-72 so revolutionary. Speed alone doesn't win wars. It's the combination of speed, stealth, artificial intelligence, and network integration that creates true military dominance. Aviation enthusiasts and military watchers have reported strange triangular aircraft at extreme altitudes, always accompanied by chase planes, always disappearing before detailed observation becomes possible. Sonic booms recorded at impossible frequencies. Radar signatures that appear and vanish without explanation. These aren't UFO sightings. These are glimpses of test programs operating under maximum security protocols. In 2021, Lockheed opened Building 648 at their Palmdale facility, a manufacturing complex specifically designed for advanced hypersonic platforms. The timing isn't coincidental. If the SR-72 is scheduled for official acknowledgement in 2025, prototype testing would be happening right now, under conditions so classified that even confirming their existence could trigger diplomatic incidents. We're witnessing the emergence of military capability that exists in its own category. Not quite aircraft, not quite missile, not quite satellite, but something that combines elements of all three into a platform that could redefine what's possible in 21st century conflict. The SR-72 isn't just the Blackbird's successor, it's the first aircraft of the hypersonic age, and everything that follows will be measured against its performance. When platforms can reach anywhere on Earth within 2 hours, traditional concepts of geographic advantage become meaningless. But the implications extend far beyond military applications. Hypersonic technology developed for the SR-72 could revolutionize civilian aviation, space access, and global transportation. Imagine passenger aircraft that could travel from New York to Tokyo in under 2 hours, or cargo systems that could deliver emergency supplies anywhere on Earth within hours of a natural disaster. The materials science breakthroughs required for hypersonic flight are already finding applications in other industries. Advanced ceramics, ultra-high temperature alloys, and revolutionary cooling systems have potential uses in everything from power generation to manufacturing. More importantly, the SR-72 represents a fundamental shift in how military operations will be conducted in the future. Traditional concepts of air superiority, strategic deterrence, and power projection are being rewritten by platforms that operate faster than most missiles can travel. In a world where information travels at light speed, military platforms are finally catching up. And when they arrive at their destination, they're discovering that all the old rules no longer apply. The hypersonic revolution has begun. America appears determined to write the first chapter. The question now is whether other nations can keep up, or whether they'll find themselves permanently disadvantaged in a world where hypersonic capabilities determine military superiority. So when Lockheed Martin finally lifts the veil on their hypersonic masterpiece, don't act surprised. You heard about it here first. What do you think? Will the SR-72 live up to its impossible promise? And how will the world respond when physics-defying aircraft become operational reality? Share your thoughts below. And if this deep dive into classified aviation impressed you, hit that subscribe button for more insider military technology analysis. Thanks for watching, and we'll see you in the next investigation.